Hello everyone. I'd like to discuss the Kendall tau distance to help you on homework 4. Now there's plenty of notes up on this on the webpage. You can get to them by going to the menu and clicking on class exercise and notes and going to week 7, the Kendall tau distance. But it's helpful to have probably something where I talk through it a little bit. So let me give you an example that's a bit like the data on the homework. So let's say that I had these pop stars. And let's say that maybe this was the ranking that I came up with. So Michael Jackson is number 1, Taylor Swift number 2, Beatles 3, Miley Cyrus 4, Nirvana 5. And let's say that somebody else has a slightly different ranking. So maybe this is my ranking. I'll say ranking 1. And let's say that there's another ranking that somebody else made, and they actually preferred, let's say maybe Miley Cyrus was number 1 for them. Taylor Swift was number 2. Maybe I already did Miley Cyrus. Maybe Michael Jackson was number 3. Oops. Maybe the Beatles were number 4. And then Nirvana was number 5 for them. So these two rankings are pretty different. These two voters are different, but how do we quantify how different they are? Well, one question we can ask is, if I picked different pairs of objects, like let's say Michael Jackson versus Miley Cyrus. In the Michael Jackson versus Miley Cyrus election, do they agree or not? In this case, they don't, actually. So let me keep track of agreements. So we call them concordant pairs. So let me make this nice and big here. Concordant pairs. And then we also have discordant pairs. And these are the ones that they disagree on. So we're going to look at all pairs. And in this case, there are 5 objects. The number of pairs is going to be 5 times 4 over 2. So there's going to be 10 pair elections to consider. So think of an election. So 10 different head-to-head contests here. So if I look at Michael Jackson and let's do them one at a time here. So Michael Jackson and Taylor Swift. Ranking 1 put Michael Jackson before Taylor Swift, but ranking 2 actually put Taylor Swift before Michael Jackson. See that? So they do not agree. So that's a discordant pair there. What about Michael Jackson versus the Beatles? Well, actually, they agree. Because see here, Michael Jackson's before the Beatles in ranking 2, and it was also in ranking 1. So if I went head-to-head, Michael Jackson versus the Beatles, they're both going to agree that they would choose Michael Jackson. So I'm going to put that in the concordant pairs list. What about Michael Jackson versus Miley Cyrus? Actually, they do not agree here. Ranker 1 says Michael Jackson is better than Miley Cyrus. Ranker 2 says Miley Cyrus is better than Michael Jackson. So that is going to go in the discordant pairs list. Okay, 3 down, 7 to go. I'll do one more and then I'll fast forward a little bit. So let's say I was going to look Michael Jackson versus Nirvana. So ranker 1 says Michael Jackson is better than Nirvana. Ranker 2 also says Michael Jackson is better than Nirvana, so they would actually agree on that election. That is considered a concordant pair. All right? So let me stop now, and I'm going to fast forward and finish the rest of the 6 pairs that I have left. So I'm going to then do Taylor Swift versus Beatles, Taylor Swift versus Miley Cyrus, Taylor Swift versus Nirvana, Beatles versus Miley Cyrus, Beatles versus Nirvana, and Miley Cyrus versus Nirvana. So let me sort all those and fast forward for a second. Okay, so finishing up here, there were 6 pairwise elections that they agree on, and there's 4 that they don't. So the Kendall tau distance is defined as the number that they don't agree with here. So I would say here that the Kendall tau between radar 1 and radar 2 in this case is 4. Okay? Now, an algorithm to compute this, I mean, you could loop through all pairs. I'm sure you could do it directly from the definition. but I want to show you how you can reduce the problem of computing the Kendall tau to sorting. So in this example, let's look at these. So supposedly there are 4 discordant pairs. Let me copy the rankings down here. And what I'm going to do is I'm going to assign a number to each one of these. So I'll make Michael Jackson 0, I'll make Taylor Swift 1, I'll make the Beatles 2, I'll make Miley Cyrus 3, and I'll make Nirvana 4. Now let me use those same numbers to refer to them down here. All right? So I'm just being consistent with the numbers that I used. So Beatles were 2, Nirvana was 4. Now, what we have in this reduction is, now it appears that I have 2 lists of just numbers. The first list is sorted already, but the second list is out of order, okay? So in the reduction from Kendall tau to sorting, what we want to do is assign numbers to the objects in the order they appear in the first ranking. Then apply those numbers to the second ranking. And now the reduction is, if I count the number of swaps a sort has to make on the second list, that should be the Kendall tau. All right? And I should say, maybe I'll specify here, I'll say an insertion sort to start with. So let's look at that. So I have, okay, it looks like I've got a list that's already sorted. That's why I chose these in order, because I don't know how to sort 2 things at once, but I can sort one thing. So let me make it look like one of them's already sorted, and then I'll just sort the other one. So here I have 3, 1, 0, 2, 4. So if I do insertion sort on this, let's do it, and let's tally up how many steps I have to do. So first, I go, first element is whatever. Second element, that is smaller than the one to the left of it, so I'm going to swap those. Okay, so now I'm finished the first 2 elements. I've done 1 swap. Now I'm going to go to the third element. That is less than the element to the left of it, so I'm going to swap them. And that is also less than the element next to it, so I'm going to swap those. So I just did 2 swaps, so now I'm up to 3 swaps. Okay, now I'm going to look at the fourth element. That is less than the element to the left of it, so I'm going to swap them. But now this element is greater than 1 to the left of it, so I'm finished. And then I go to the last element here. Oh, and I should have recorded, I did 1 more swap there. I go to the last element here, and it is actually greater than the one left to it, so I'm finished. So let's see, I just did insertion sort. In the process of doing insertion sort, I counted how many swaps I had to do. That was 4. Did that agree? Yes, it did. I had 4 discordant pairs up here. So that's the algorithm for computing the Kendall tau distance naively. So I say it's naive because actually this is an O of n squared algorithm for computing Kendall tau distance on n objects. All right. So that's fine. That takes you through a good part of the assignment there. And that also, what's cool about this is an example of a reduction, which is an idea that happens a lot in algorithms. Oftentimes you can show that an algorithm that you already have can be used to solve a new problem that you want to solve. Okay, one thing that's kind of interesting here is actually if the rankings are exactly the reverse of each other, then there are n times n minus 1 over 2 discordant pairs. So in the example above, where I had n equals 5, so I had 5 pop stars, that would be the idea is that this is all pairs. So 5 times 4 over 2 is 10. So in other words, if these are complete reverses of each other, all 10 of the pairs would be discordant. And so the Kendall tau distance would be 10, or n times n minus 1 over 2 in general. So it kind of makes sense that an algorithm to compute this directly would take big O of n squared, because n times n minus 102 is big O of n squared. All right? But since we've reduced this to sorting, we can try to use a more efficient algorithm. We'll say big O of n log n with merge sort. So that's what we're going to try to do. What this means is we'll have to count more than one swap in one step. Otherwise, we could have a case where the Kendall tau distance is supposed to include n squared swaps, n squared discordant pairs. But we're going to have to count them faster than that. We're going to have to count multiple swaps in one step. So let me show you an example of this, and I'll explain how merge sort can do that more efficiently. So let's say that I had the rankings, let's say maybe 0. Okay, so I'll use 6 elements. I'll say maybe 1, 3, 4, 0, 2, 5. Okay, let's try that. Just a little bit bigger here. All right, so we're going to do merge sort now. Notice, we're at the point where the left half of this is sorted and the right half of this is sorted, and now we just need to do the merge. So the merge is going to look at these and say, okay, 0 is less than 1, so I'm going to take the element from the right-hand side first, put it in the staging area, right? So that is my first step there. What's interesting is every time I take an element from the right half, that element jumps past, really jumps ahead of a bunch of stuff to the left, right? So if I were going to do this with insertion sort, I would sink 0 down one step at a time. But actually here I can notice that, okay, 0 is coming in front of 3 numbers before it. So actually, I could just in one step say plus 3 when I put 0 in front of 1, 3, 4. All right, so in that one step where I take 0 and put it in the staging area, I add 3 swaps. Okay, and then I move this forward. All right. So now I'm going to take something from the left side. 1 is less than 2. So 1 is going to go in the staging area next. Actually, there nothing happens. Nothing special happens because 1 is not jumping in front of anything that it's less than. Okay. Now I'm going to look at this and I'm going to say, oh, 2 on the right side here is less than 3. And so 2 is going to go into the staging area. And what I notice is the 2 jumps in front of the 3 and the 4, right? The 3 and the 4 haven't come in yet. So I look at the elements that are still left on the left side, and there's 2 of them actually. So I would say I get a plus 2 when I put the 2 in front of the 3 and the 4. Okay, so I'll do that. I'll move this along here. Next, I compare 3 to 5. 3 is actually less than 5, so I'll take the element from the left. That does not incur any cost for a swap. So I'll put the 3 in there, move along. 4 is less than 5, so I'll put the 4 in there, move along. That is not jumping in front of anything. So I do that. And now I've run out of stuff on the left-hand side, so I just take what's left over here, and nothing, no swaps to count at all there. So the 5 ends up at the end. So supposedly, in this merge step, I was able to count 5 inversions, or 5 swaps. So let's see, would insertion sort have given me 5? Let's just check that real quick. 1, 3, 4, 0, 2, 5. So if I were to do insertion sort on this, then, okay, I'd start at the beginning here. Nothing happens to the first element. Look at the second element. That's okay. That's greater than the one to the left of it. Look at the third element. That's okay. That's greater than the one to the left of it. Look at the fourth element. Okay, 0 is less than 4. So I swap that. That's one swap. 0 is less than 3. Swap that. That's one swap. 0 is less than 1. Swap that. That's another swap. So I just did 3 swaps to sink that 0 down to the correct spot. So I just did 3 swaps. All right, so now I go here. This doesn't have to swap anything. Now I see the 2. And that is less than the thing to the left of it. I do a swap here. That is less than the thing to the left of it. Do a swap here. So that was 2 swaps. Now finished. And 5, that's in order. So yes, that gave me the same answer as insertion sort. Okay. So for the efficient algorithm to compute Kendall tau, the full reduction is come up with these numbers, right? Number the first list as if it were in order, then use those numbers to create numbers for the second list, and then apply merge sort, and I will count the number of inversions, or the number of swaps that insertion sort would make on an equivalent sort. Every time I take something from the right half and it jumps the line in front of greater things to the left of it, I count the number of swaps the equivalent number of swaps that insertion sort would have made there. And the reason that's more efficient is because I can count them all in one step. All right, so that is probably the trickiest part of the homework, is doing that full reduction, making it efficient. But for the first part, you just run insertion sort. That's a little bit more straightforward there. Every time that you do a swap, you add 1 to the number of discordant pairs. Okay. So the only other thing that I need to explain is the Kemeny optimal rank aggregation. And this is kind of exactly the same thing. The only difference is now instead of having, comparing one ranking to one other ranking, we're going to compare one ranking to everyone's ranking. So I'm going to try to compare my ranking to everyone else in the class's ranking. And my goal is to minimize all disagreements with everyone. So in other words, I'm going to try to minimize the sum of the Kendall tau distances between some permutation that I'm trying to figure out and every rater in the class. And so what that ends up doing is minimizing the total number of disagreements in all pairwise elections between my ranking and everybody else. And so what you see in the homework is that is going to give you a slightly better answer than if you did this average rank aggregation between everyone. So this, for our class, this gives us 299 disagreements versus 303 doing something a little more naive. The problem is you have to consider every permutation, so it's not very efficient. But this will give you some practice using recursive code to enumerate permutations. All right, but the meat of it, most of it, is in computing the Kendall tau distance. So you do that with n squared first, and then you can do this reduction that I was talking about here with merge sort, where you keep track of the number of inversions as you're doing the merge, and then you add together the total number of inversions. All right? So here it actually gives you the pseudocode, and then I went through the example to show you when you actually count inversions in the merge sort. All right, so I hope that helps. Let me know if you have any more questions, and I hope you have fun with this assignment. This has been one of the favorites in the past. So enjoy.